Okay, thank you. Good morning, and thank you to the organizer for this opportunity. I'm Lorenzo Chicchi. I'm a PhD student here at the University of Florence. And I'm here actually from the beginning of this workshop, and I heard a lot of talks, very interesting talks on how we can apply some machine learning techniques to different areas of physics. But today I'm going to tell you maybe something a bit different, something related to what Lorenzo Ciampagli talked in the last talk of the last week on Friday. But don't worry if you were not here last Friday, you can follow this talk. And so, as a research group, we are a group of physics of complex systems. In particular, we are interested in network theory and in dynamical system on network. So we started to be interested in artificial neural network from this point of view. And our goal is to include in these very important tools what we know about network theory and what we know about dynamical systems. And in particular, today, I would like to show you this new model we formulated that is called a recurrent spectral network. So I will start this presentation with a very brief introduction to how we can reformulate the feed-forward architecture in a spectral formulation. This was the topic of the last talk by Lorenzo, so I will not spend much time on this, but if you are interested in that part, you can ask me or Lorenzo during lunch or after this talk. Or also, I think you can see the talk online. Then I will make an overview on the recurrent neural networks that is the architecture we faced in this work. And then I will finally introduce our model called recurrent spectral network and a new version of this model that is called complex recurrent spectral network, on which we are working on actually now. So this last part is essentially preliminary results. Okay, so let's start with the brief introduction. So we all know what neural networks are. Neural networks are very important, very useful tools to approximate very complex target function. And the most common architecture, the most used one, is the feed-forward architecture. That is the one shown in this animation. And in this architecture, the nodes are organized in different layers. So the signal, the input enter the first layer, and then the signal is propagated layer by layer until it reaches the last layer where we compute the loss. And when we say that we train the network, it means that we tune the weights of the network in order to minimize a loss function compute in this last layer. So from a mathematical point of view, a feed-forward architecture is just a subsequential application of some linear transformation described by some matrices W, and the application of some nonlinear functions in each layers. So recently, a new formulation, the kind of architecture, has been introduced by some of my colleagues. And again, this was the topic of the last talk, so I'm not going into the details, but the main idea of this work is to reformulate, or better, is to work not with the direct space matrices W, but with a spectral decomposition. So the idea is to rewrite the linear transformation, not with just one matrix, but with this decomposition, a spectral decomposition, in order to have some parameters like eigenvalues, eigenvectors, and so on. Well, this is not a trivial task for a feed-forward architecture because each layer transfer is described by a rectangular matrix. So it's not easy to define a decomposition. However, the authors working on the framework so they decided to describe the linear transformation inside the feed-forward network by looking at the global network. So they used they had these big matrix that describe all the network, and so all the linear transfers inside the network. And under this framework, they introduced a new a suitable basis with a particular structure that allows to obtain, when we use this basis in the spectral decomposition, a matrix in the direct space that is not exactly the adjacency matrix of the feed-forward neural network, because we have some more elements, so some more links. But what is important is that the action of this new matrix is the same of the action we want for a feed-forward neural network. So with this new formulation, it is possible to define different things. For example, it's possible to define new training strategies, or also it's possible to use the eigenvalues of this decomposition to define some ranking of the nodes and to define some pruning strategies. Well, all these things are in the talk of Lorenzo Giampagli, so I suggest you to see the talk if you were not here last Friday. However, when so the difficulty of define this decomposition is due to the fact that the matrix inside the feed-forward, the matrices inside of the feed-forward architecture are rectangular. But we know that there are others architecture in neural networks that are described by square matrix and are more easily to be decomposed. And so we started to be interested in the recurrent neural network. The recurrent neural network, there are a lot of models of recurrent neural network, but in general, the main, the general idea is that we introduce a certain time in this network. So we have some iteration of the same network, and the network is described by this box in the general idea. So this unit, and the network takes as input a vector x that can depend on time. So we can have a different input at each time step, or also we can have an input that does not depend on time. So we have an input vector just only for at the first step. And this unit take as input also another vector that is the internal state vector. And as output, we have the output vector that can be different on each iteration, and an upgrade of this internal state vector. So we can also see this network, this architecture, by unrolling in a certain way, by remove the time and describing the network like this. But what is important is that these units are exactly the same. So there are exactly the same parameters and so on. Okay, so what define the neural network are what inside of this box, and there are a lot of different models. This is one, is the LSTM model. So this is what inside a LSTM neural network. So as you can see, this is the input vector, is the internal state at the previous time step. This is the upgrade of the internal state. and this is the output vector. And as you can see, inside a neural network like this, there are a lot of things. There are feed-forward neural network included inside. There are some gates by which we can do different operation. And so from a point of view of a physicist of complex system, this is a very complicated model. So we actually are not interested in this kind of very engineered model. And we are interested in very more simple models. And in particular, we are interested in the simplest recurrent neural network we can think. And this is in a certain way, the simplest recurrent neural network we can define. So inside this, the box, there is simply a layer transfer. So the application of a linear transformation by a matrix W that is applied both to the input vector and the internal state vector. So another way to see this is that we sum the internal vector with the input vector, and then we apply the linear transformation and a nonlinear function that in this case is an hyperbolic time. And as output, we have exactly, so this is the rule by which we upgrade the internal state, and the output at each time is exactly the internal state. So if we consider the most simple case in which we are where we are an input that does not depend on time, so only on the first step, on the first time step, we have an input. All these things is a very complicated way to describe a very simple things. And so that this architecture. So we have an input that enter a fully connected network. Since in the simplest recurrent neural network, we have a layer transfer that is described by a square matrix. So we can see this as an adjacency matrix of a fully connected network. And so the input enter the network, and then the network evolve by applying this matrix W and the nonlinear function on each iteration. And then we define a certain number of iterations after which we compute the loss. So we consider the output of the network, the internal state of this network that we have K star iterations. Okay, this is very simple. And as I said, we now have the same matrix on each iteration because we don't have any more layers, but we have iterations. And this matrix is a square matrix, so it's very easy to decompose it. Okay, now we have all the knowledge to present our model, the recurrent spectral network. And the main two ingredients of such a model are the following. So, as I said, we work with the spectral decomposition of the matrix W, or better, it's better to say that we don't work with the direct space matrix W, but we describe the linear transformation by using this decomposition. And we put some constraints in this decomposition. In particular, we fixed to one some eigenvalues, and we bounded the others to have a magnitude lower than 1. So I will refer to the eigenvectors relative to the first eigenvalue, so the fixed one, as recognition eigenvectors. Okay. So now we have again new trainable parameters that are the eigenvalues not fixed 1. However, they have to be bounded during all the training procedure, and also the relative eigenvectors. These are the new trainable parameters. The second ingredient for this model is that we ask the nonlinearity to depend on time. And in particular, we want that nonlinearity vanish in time. And we can do this in two different ways. First, we can impose this vanishing in time by hand, by the nonlinearity for a suitable term. Or we can also, but this second way, we explore it, but then we didn't decide to use. But however, for completeness, the second way we can impose this dependency on time, this vanishing on time, is to use another neural network to approximate the nonlinearity we want. So just for completeness, what we found with this second possibility is the following. So we can also decide, yes?
Sorry, may I ask something? The previous slide? The previous slide? Sorry, I don't know anything about recurrent neural net. So you train in the same way you train usually, like with backpropagation?
Yeah.
That's the way.
With the backpropagation.
But then just the interactions, the way you do? Because you have you said you have the same W's, right? No.
Yeah. So we have the same W. You essentially, you can see the recurrent neural network. So this simple recurrent neural network as a feed-forward with the same, exactly the same metrics. So you have only, when you, how to say, you compute the gradient on each iteration, and you for each parameters you have a gradient. You can you simply apply the backpropagation like in a standard feed-forward. In this simple case, for more complex architecture like LSTM, I actually don't know how the gradient, but I think there are not very many problems on it. Okay.
And one more question: what's the psi-r and psi-t?
Okay, so I divided the basis into part because the psi-r are the eigenvectors. That I will refer to these first eigenvectors as recognition eigenvectors because they are the eigenvector associated to this first set of eigenvalue. And then I will explain why these eigenvectors are important, because as you can imagine, since these are bounded to have a magnitude lower than 1, if you repeat these metrics, this linear application, so without considering the nonlinear function, the system will converge to a linear combination of these first eigenvectors. So this is why we divided these two eigenvectors. Okay.
Sorry, maybe it will help me to understand a little bit. So you're applying this recurrent neural network to a time-independent input, you say?
You can apply.
So it's not a time series.
You can also apply to a time series by adding.
Yes.
Okay, by adding. So this is. Let me skip again. No, okay, this is just for an example, and actually we use this data set. So we use a data set that does not depend on time. So we have just one input. We have the input only at the first time step. But you can also think to use this kind of architecture to analyze time series by adding a new input to the internal state to each at each time step. So these kind of architecture are not too many are not so useful because as you can imagine, you have a problem of vanishing. So they are not able to to preserve memory. Okay, so for the time series are not so useful this kind of very simple recurrent neural network. Okay, but with in the spectral domain, there are some other properties that we can use. So as I will show you, there are some differences. Okay. Yeah, it's not so. Yeah. Okay. So this is just for completeness. These are the function, the nonlinear functions that we can approximate using another neural network, and we can do this in two ways. We can ask the neural network to approximate the nonlinear function g, and again we impose the vanishing on time by end, or we can also ask a neural network to reconstruct to find the best nonlinearity for this kind of problem, asking also so with also the time dependency. So, and as you can see in the first case, we found something that is similar to ReLU, maybe, however, a threshold function. And in this second case, we found a nonlinearity that is essentially an hyperbolic tangent with some shift in the time step, so that in a range of the input, we see a sort of a vanishing time. However, as I said, we have decided to work in the in this first under this first hypothesis. So we simply use a hyperbolic tangent, and we impose the vanishing time by end. So, however, what we have now, we have a complete, a fully connected network with a particular structure with some constraint on the eigenvalues, and we have also a nonlinearity that vanishes in time. So after enough time, the dynamics become linear, and so we can use all what we know about linear system on network. As I said before, what we have is that regardless of the values of the trainable parameters, what we will have after enough iteration is that the state of the network will be a linear combination of the recognition eigenvector 5R. And we can have two possibilities. The first is to fix these eigenvectors a priori, or we can also think to include these eigenvectors in the trainable parameters, so that the network learn what are the best vectors to be used as attractors. And so now we can define a classification task by simply asking the network to associate a specific attractor to each of the class of the classification problem. And in particular, we decided to use the simplest possibility, so that we associate each class of the problem to a specific recognition eigenvector. So instead of having a linear combination for each class of the classification task, we have one of the recognition eigenvector. This is just a possibility. And then we define a suitable loss. So essentially, we ask that after k star iterations, we want to have a final state that if we write it on the basis 5, in this decomposition, we want to have all 0 coefficients, but one that is the one associated to the class of the corresponding input. So in other way, we want that if we put an input inside the network evolve and the state collapse to one of the recognition eigenvectors. So
you go. So can you go back, I think, 2 slides? Yes, no, that's good right there. I'm just trying to understand this. This seems like there is this vanishing of the nonlinear functional limit here. This turns into PCA, right? This thing finds this limit, it just becomes the PCA of the input.
I don't know.
It's a linear regime. You're acting to find the dominant.
So probably yes.
eigenvectors.
I don't know. I would like to discuss about this because I don't know. But this is a way to use the nonlinearity that is very important for classifying. So in this kind of problem,
That's the part I'm trying to understand. So we're on the way, I think, to just doing PCA, but there's something important perhaps about that journey, how we get there. And so maybe you can comment about, I mean, this limit is interesting, but if it's just PCA, it's less interesting. So are we stopping before we reach the PCA limit, or what's happening?
so the idea probably so we use the nonlinearity. I mean, if you start at the initial time, you have the nonlinearity, and you still have for some iteration. So in a way, you divide the data set. But then we want that this model that become linear, because we want to use then some property of the linear of this linear
Okay,
system.
so maybe it breaks, the nonlinearity is able to break up the input space into subspaces onto which PCA is done there, separately from all the others.
This probably is a good way to think this.
Okay,
I don't,
I'll go.
I don't know if you.
I'd say that I'd say that no, I mean, I think you're true in the sense that in the end he's doing basically the PCA, but the most important part of the classification, I think, happens in the nonlinear regime. Am I right? I mean, you have the nonlinear part, which you go in a higher dimensional space, and then after that, slowly try to converge to a linear system. And I think what basically we are forcing in find the principal components of the signal. But
it does something non-trivial if it's able to pick out parts of the space and perform PCA on them. That's a good trick. Right? That's definitely a good trick. So obviously doing PCA globally is not a good trick. But I'm not saying, I don't think that's what's happening. I think it's this trip through the nonlinearity is doing some breaking up of the input space, and PCA is perhaps being done separately on each.
yeah, I think you're right. Yeah, I agree.
Okay. So
Okay. Other questions?
Whatever. So as always, you need in some sense to reinterpret your recurrent neural network.
Sorry, I didn't hear.
In some sense, you need to reinterpret, I mean, using your spectral formalism, you need to reinterpret your recurrent neural network as a feed forward, you said, in some sense. Let's say you need to build a map. So this, let's say, decaying the nonlinearity that you're imposing, right? So can I, in principle, interpret this thing as having a feed forward neural network where the first layer is highly nonlinear, and then it's decaying towards the final layer, which becomes linear?
Yeah, exactly. Okay. Okay. Okay, we try tried our model on this very well-known MNIST data set. So we are in the case we have just one input. So we have the input only on the first iteration. This matrix here is a simple represent the rule we decide to use to enter the input on the recurrent neural network. This can be simply mapping one neuron to one neuron or some random linear transformation or whatever you want. In this case, we use this is because in a certain way with this initial linear transformation, you can separate the sides of the recurrent neural network to the sides of the input. You can use a larger recurrent spectral network or a smaller one. However, this is not important, very important. In this particular case, we decide to use a recurrent spectral network with a number of nodes equal to the number to the size of the input. So we can represent the network by using an image of the size of the input. So they will see the activity on the network by looking a picture. And so we just for help the visualization, we decided to use as eigenvectors, the recognition eigenvectors, some vectors that can be shaped in order to manifest as a serialized version of the number to be classified. So each 4, for example, to collapse to this final state. And as you can see, different example from the data set, iteration by iteration, collapse to what we want to see inside the network. So we can have a possibility to decide what the final state has to be. Okay. So let me spend very few words to how the eigenvalues are involved in this procedure. Just be clear, this evolution is the evaluation, is the process of the network. So the network is trained, and we put the input inside the network, and we see how the activity on the network evolves. So during this process, the eigenvalues are involved in different way, in different time. And so to evaluate how the eigenvalues are involved, we define 3 different sets of eigenvalues. The first set is the 10 eigenvalues associated fixed to 1. So what we can call the memory of the network. Then we have a second set of eigenvalues that are the larger eigenvalues, but smaller than 1. And then the third set are the 10 smallest eigenvalues. Again, these eigenvalues are fixed because we are considering a trained network. Here, you are fixing also depending on vectors. Yeah. Yes, fixed. Is exactly this situation. So the eigenvectors are fixed. Yes. Yeah. And then we consider 2 classes of the classification task. We want to estimate a sort of distance of these 2 different families in time. How this distance evolving during the time, the iterations in the 3 subspace defined by these 3 different sets of eigenvalues. So each of these set define a subspace. So we want to see how these 2 family of inputs are separated inside these 3 subspace. And as you can see, the maximum distance in these 3 subspace is reached in different moments of the of the evolution. This is a sort of how, because now we are watching on the evaluation process like dynamical system. So we want to see how this system evolve. And as you can see, the fastest eigenvalues, that are the smallest ones, show a peak in the distance that are during the first time step. And while the second set show a peak after some step, and obviously the recognition, the first set of eigenvalues that are the fixed one and the one equal to 1 show a distance that grow iteration by iteration, because in this subspace we have the final separation of the data set. So with this formulation, we can interpret the evaluation process of the network as a dynamical system, and we can do some analysis like this. Okay, so this model.
May I ask you something?
Yeah.
Back to the previous slide. So if I need to find a physical interpretation of this system, I would say that the orange eigenvalues are the lightest modes, while the blue ones should be the heaviest. So I would expect the system to first learn the heaviest modes. So first the blue ones, then the green ones, then the yellow ones, because those are also a little bit, I would say, stochastic, even though maybe it's not appropriate.
I don't know, because these, I have to say, I mean, in a certain way, these eigenvalues, iteration by iteration, I have to say, goes to 0. Okay? Because in every iteration, you have a sort of multiply them by themselves and so on. So they can be used certain way only on the first iterations, because then they vanish. And so in a certain way, the smallest eigenvalues are the one that can be involved only during the first iteration, because then they are the dynamics collapse in that directions, and so you don't have any possibility to separate the data set in that part of the space.
What's your distance measure?
So, sorry. The distance is a sort of distance of the, so you have two classes of inputs. So for example, the 4 and the 5 digits, and you compute the distance between these two classes, of the average distance between these groups of these two groups of inputs. So it's a sort of distance of the paricent. Okay. Distance. Sorry.
Your bar is just Euclidean distance somehow between centroids of these two places, or?
No, we compute the distance between each couples, and then we make the average.
Euclidean.
Sorry.
The norm.
Yeah, R2. Oh, sorry. You see, the L2. Yeah. Is okay. This is an important property of the recurrent spectral network, because this recurrent spectral network become linear. So if you plot the accuracy of the recurrent spectral network on different iterations, and if you compute also the accuracy on this standard recurrent neural network, as you can see, the standard recurrent neural network show an high accuracy only when the number of iteration matches the number of iteration you did during the training procedure. So you have to know what is the number of iterations used during the train. While for a recurrent spectral network, since we enter this linear regime, you have that the accuracy grows during the first part of the iteration until you reach a good level or a good level, and then it maintains height also for a number of iterations after the one the number we use during the train procedure. So in a certain way, this means if you have a trained recurrent spectral network, you can simply apply to the input and wait enough. Okay, this is just the first property of this kind of model. Another thing we tried to face is the problem of sequential learning. The problem of sequential learning is consisting in so we want to train the network, the same network, on two different data sets in a sequential way. So we want to first train the network on a first data set, and then by starting with the final state in terms of weights we have after this first training, we want to learn the second, we want the network, we want to train the network on this second set, okay? And we want that the network does not forget the first data set, okay? So we tried to face this problem with by imposing a sort of quasi-orthogonality in the basis 5. So we use these parameters epsilon to impose this quasi-orthogonality, and in particular, if epsilon is equal to 0, the task is not so so the structure is not so interesting, because we have two separated the networks in the direct space, while if epsilon is lower than 0, we have a fully connected network in the direct space, while we have this sort of quasi-orthogonality in the reciprocal space. And then we organize the eigenvalues as follows. We have these first 5 eigenvalues fixed to 1, and a first set of trainable eigenvalues, and then again 5 eigenvalues fixed to 1, and the second set of trainable eigenvalues. Then we define this procedure. First, we train the network on the first data set by acting on the first set of trainable eigenvalues and on the relative eigenvectors. And during this phase, we turn off in a certain way the second set of eigenvalues equal to 1. So we fix them to 0. So this means that I have to say, only a part of the memory is accessible to the dynamic. So we train the network on this first data set, and then we start to train the network on the second data set by starting on with the parameters we obtain after the first training, and we do exactly the same things. So we turn on, we switch on the second part of the memory, and we turn off the first part of the memory. And when I say memory, I mean the eigenvalues equal to 1. And after this second training, at the end, we turn on all the ones eigenvalues, and so now the memory is all accessible. What we found is something like this. So in the first panel is show what typically happen with a standard neural network. We use the recurrent neural network because the simple recurrent neural network, because it's the model more similar to the second one. But this is just to show what is the catastrophic forgetting. So in red, we have the accuracy on the first data set, and in the blue, we have the accuracy on the second data set. And as you can see, when we start to to train the network on the second data set, the two accuracies switch. So the accuracy on the first data set goes to 0, while the accuracy on the second data set grows. Okay, this is what is typically called catastrophic forgetting. While if we use our procedure, what we found, obviously the first part of the training, so when we train the first data set is exactly the same. But when we start to train the second data set, what we found is that the accuracy on the first have a sort of drop, but at the end, the two accuracies are more or less the same, even if they are not at their maximum level. So this is just to see how we can use the spectral formulation to impose, to define some particular procedure that we can.
Yeah, you are protecting the part of the memory.
Yeah. No, this is not a comparison. I mean, this is I mean, this is not a comparison because it is unfair. We all know that if you take a neural net.
Where you impose the and you don't protect them. You still have the same catastrophic predictive. You try this.
Yeah. So if you don't eigenvalues to zero, yes, because in the second part, in a certain way, you will find some trainable parameters. So, for example, these eigenvalues that are magnitude higher than the first set, because first of all, the network in that case learn to go in this part of the memory, and this is very simple. But if you add a factor 10 on these eigenvalues, is essentially the same thing you have if you turn off this part. So and this is not what we want. In a certain way, we have to say to the network, okay, you have to store this data set in this part of the final subspace. Okay. So it's very important to impose these. Okay, so this is the recurrent spectral network model, and then we are now we are working on a new version, let's say, of this model that is called a complex recurrent spectral network. As I said, essentially the two models are more or less the same, but we have some differences. Okay, what are the new ingredients or the differences between the two versions of the model? First of all, now we work with complex eigenvalues. So we still have the fixed eigenvalues with these that have a magnitude equal to 1, but now they are complex exponential. So to each eigenvalues, we can associate a parameters t that is a sort of period. And then we decided to remove the vanishing in the non-linearity, because if you use a non-linearity that depends on time, you have to define an initial time where the non-linearity acts, and then they begin to vanish. Okay. And we decided to confine the non-linearity in a part of the space, or better, in a subset of nodes. So in a certain way, we have a fully connected network with a part that is a non-linear part and a linear part that is the rest of the network. And as a third ingredient, we ask that the attractors of the dynamics have to be confined in the linear part. Okay, so the only non-zero components of the recognition eigenvectors have to be in this part of the network. So we again work with the spectral decomposition of the matrix W. We have exactly the same structure. We have these trainable parameters, but now the eigenvalues are complex eigenvalues, and they are not anymore equal. So that that means that every eigenvalues is associated to a specific period t. And when I said that the recognition eigenvectors are confined in the linear part, what it means that we want that these eigenvectors have non-zero components only in this part, since we can associate each row of these eigenvectors to a specific node. And so if this is the part where the nonlinearity acts, we want that these eigenvectors have non-zero component only in this part. And in particular, we impose this specific structure. So the recognition eigenvectors share this last neuron, this last component, and then we have this sort of diagonal with 1. So each eigenvectors involve the last neuron and another neuron, and then it will be clear why we use this structure. Okay, now that the non-linearity is always present, we cannot say that the dynamic will converge in the subspace of the recognition eigenvectors. But what is important is that if the dynamics go in this subspace, so if the activity on the network can be described as a linear combination of the recognition eigenvectors, so also at the next step, the activity will be in the same subspace. And this is because if you apply the rule, the upgrading rule, you have the multiplication for the corresponding eigenvalue. But then when you have to apply the nonlinear function that can bring the activity outside this subspace, since these eigenvectors have non-zero component only in the linear part, this nonlinear function is not applied. So in a certain way, we have now not a linear an interval of time where the dynamics is linear, but we have a region of the network that is linear. And once you are in this part of the network, you'll stay in this part. And this is true also for obviously for the next step. And so after a time t, you will have an activity on the network that is of this form. Okay, so since we have complex eigenvalues, we have to pay attention because also these coefficients will be complex, so we can write them in this form. And remember the particular structure of the recognition eigenvectors, and in particular the fact that they share the last component. Okay, so if we compute, we make some calculation to compute the activity of the last neuron. I mean, so the last component of the activity vector that, as I said before, after t star plus t iteration will be will have this form. So since this component is equal to 1, you can do some calculation. For example, you can write the coefficient with the real part plus the imaginary part, and so on. And at the end, you will obtain the real part of the activity on the last neuron plus the imaginary part. And if we focus us on the real part, we will see that this model allows to have an activity, a real part of the activity on the last neuron that can be written with this sum. So we have a sort of Fourier series on this last neuron. Okay, and now we redefine the classification task by asking the network to learn how to associate to each element of the data set the corresponding function of time in the real part of the last neuron activity. So where this is the real part of the last neuron, where is explicit the fact that it depends on the input and on the weight, so on the trainable parameters of the system. Okay, this is just the loss we use. And so another way to see this problem is that we are asking the network to learn the coefficients of this decomposition by using as a basis for these functions some sinusoidal functions. Okay. I said a lot of mathematical stuff, but I want to be sure that is clear what happened in the direct space. So this is just an animation to see what happened in this in the direct space when we use this kind of model. So this is the linear part of the network. This is a representation of the network, and this rectangular is the linear part of the network, and where there are the recognition eigenvectors, and the input is enter the first part of the network. This is important because if you want to separate the data set, we have to use the nonlinearity, so we have that we need that the dynamics for a certain time has to be in the nonlinear part. Okay. While in this plot is reported the target function for the same class and the real part of the activity on the last neurons. Since the eigenvectors, the recognition eigenvector have this particular structure, and so each eigenvectors involve the last neuron and another neuron. These are the 5 neurons used, so involved in this case. And so in each of these neurons, we will see the one of the sinusoidal function used to reconstruct the final function. Okay, so if we start the animation, we see that the activity flows toward the linear part, and if I stop it, so this is the window where we have computed the loss. So in a certain way, we force the network to reproduce this function during these time steps. These are one of the components used by the network to reproduce the function F4. And if we go on, you see that also for time steps after the one used during the training procedure, the function is well reproduced by the network. Okay. So this is what happened in the direct space. And actually, this is what something we like for as physicists interested in dynamical system on network. Okay. So some properties of this new version of the recurrent spectral network. First of all, it's no longer necessary to define an initial time t0 because the nonlinearity is does not depend on time. So you can also evaluate very long time series, for example, because you have not to restart the nonlinearity. Then it still has the property of preserving memory, like the first version. And due to these two properties, we have a third property, that is that this kind of network can process multiple input in sequence. And this is because the information is stored in the linear part of the network. And if we focus us on this last point, this is just the final part. So we consider to have a trained complex recurrent spectral network, sorry. And so the network is able to reproduce for each element of the data set the corresponding function of time, or at least almost for almost all of them. Okay, because the accuracy is not 100%, but is very high. Okay, and then we consider the following scenario, where we have a first element of the data set that is evaluated by the network. So after enough time, we will be in this subspace defined by the recognition eigenvector. So we have an activity of this form in all the network. And then at that time, we add a new input by simply sum it to the activity that is present in the network. So without resetting the network. And then if we upgrade the network with a time iteration, we will have that the nonlinear function is applied only on this second part of the activity, so the one related to this new element of the data set. Okay, and so in a certain way, we divided the two dynamics, the one of the activity that was present in the network, and the dynamics related to the new input. Okay, again, another animation to see this last property. So we have now a new input and enter the network at the initial time. And so we see exactly the same things as before. After some iteration step on the last neuron, we see the relative function we defined for the class of the input. Okay, it's a bit slow. And after some time, no matter when, we decide to enter inside the network another input. I made the animation too long. Okay. Okay, so as you see, as you can see, the function is well reproduced also after the iteration use. Okay, so after a certain time, we enter another, we put another input in the nonlinear part of the network. And in this plot, if you can see, there is still the red line that is the function related to the class 7, and a green line that is the sum of the function related to the class 7 and the function related to the class C6 computed in a time after, so with a certain phase, so some time shift. And as you can see, after some time step, we have that the dynamics, the activity show exactly the grid line. So what does it mean? It means that essentially in this linear part, the classification are summed. Okay, and we have a lot of information in this kind of a function of time, because we have the information of the two distinct input, but we have also the information of the time shift. So we also there is also the information of a sort of the distance of time between the first input and the second input. Okay. Okay. In conclusion, we saw how the spectral formulation can bring to some new model of neural networks. And we saw how recurrent spectral network in particular cannot model like this cannot be obtained by working on the direct space, because we needed to put some constraint on the reciprocal space. So we I have introduced you to this new version, but again, these are is just a preliminary result on this complex recurrent spectral network, and I hope we will finish this this part as soon as possible. And at the end, we saw also how we can use this second model to elaborate multiple inputs sequentially. Okay, but and last, maybe this is not so important for those who use neural network as tools, but as a physicist of complex system, we are also interested in this, all the models that are bio-inspired. And so we all know that neural networks are models that are very different from what a brain is. But if we want to go in that direction, and as a physicist of complex system, we want to do it, we have to introduce the dynamic also in the evaluation process and not also in the training procedure. So that's all. Thank you. These are the references, and these are my collaborators. Thank you.
Thank you for the seminar. So we had several questions already, but if there are other ones.
So just to see if I've it right. So in this last part with the complex recurrent spectral network, that doesn't refer at all to inputting complex data. It's entirely about playing with the representation, allowing complex eigenvalues to exist inside your representation. Okay.
Yes, maybe it's not, I mean, especially this second part, this second version of the model, probably is not very useful if you want, for example, a model that is fast in the training procedure and so on. But we, as a research group, we are also interested in obtain some more bias behavior in trainable network. So without losing the possibility of train this network, and without losing the possibility of using this network for some task. However, maybe some of these property we found could be useful in some application, because, for example, I don't know if you want a network that are unsupervised also in the evaluation process. So some, I don't know, tools that have to find some trigger events or something that happened on a specific, so I don't know, maybe not, but just to be clear, we are interested in develop some theoretical models that are also more bio-inspired, and so that show some behavior that can be also more interpretable from a point of view of a dynamical system, also in the evaluation process. So this is our background, and also some motivations for this kind of works. Okay.
So in that second part with the complex network, is it possible for me to just decompose it into the real and imaginary networks, and they're kind of talking to, they're interacting in some way, they're beating against each other as they're doing the problem? I mean, I'm trying to understand why the real version of the system didn't, the non-linearities decayed away, as you said, but that didn't seem to happen. And the complex network just seems to have very different dynamics, right? So I guess I'm trying to understand why. What's different, other than it's complex, and it's almost like two networks interacting in some way.
Yeah,
that's hard, that I don't quite
actually
see.
To be honest, we have to explain the role of these, of the complexity in sense of complex number in this kind of network, because we are interested in that part, but we didn't do for the moment. Okay. For example, we we looked only on the real part of the activity, but maybe on the imaginary, also the imaginary part could be interesting and so on. So it's a very new model, new version. So we have a lot of work to do.
Other questions? Okay, if not, let's make Lorenzo again.
Thank you.